Unfortunately, it was multiple choice, and so I don't think I did particularly well because I thought of all those other things that I believe they were ignoring, such as it's an ideal room. So, or they were assuming it was an ideal room. All right, let's go through the steps. Force diagram. Now, we really only care about the force diagram of the two masses. It's an ideal rope, I don't have to worry about that, but we can put the other things in there, just ideal pulley as well. This is part of the ground. All right, so what are the forces acting on the 5 kilogram mass?
The normal force
Acting
upward from the mass onto the box.
acting upward on the mass from
The thing is
the thing that's on, okay. So we have the y. I'm gonna put a little 5 down here just because it's the 5 kilogram mass and I like my subscripts to have something to do with the problem. And then down here, 5. All right. What else?
Acting downward.
The rope and the pulley.
Okay. Y sub R. Y sub R. Normal force, I think we're done. Because we have the 5 kilogram touching the, whatever it is, the surface touching the dais, podium. And we have rope and pulley. All right. What else?
Tension.
Okay. At each end, so I got a tension pull in here, a tension pulling here, a tension pulling here, a tension pulling here. At this point, it is critical that we realize that it is an ideal rope, and the tension is the same magnitude at each end. I've had some students put subscripts in here, and that's not inherently wrong. And then they go to solve it, and they have an extra unknown, and they fail to take the leap that FT1 and FT2 happen to be equal in this problem. All right, so tension, I have only one rope, I've taken care of both ends, done.
gravel. Like that box going down.
What's the force?
Weight.
Okay, so I have weight acting on, you were saying this box?
Yeah.
Anything else?
And I guess that weight of the other box too.
Take away the word I guess. I know.
I know the box is weighing on the thing.
5 and since this is part of the ground, put it there, right, put it down there. So we're left with other and friction.
Are there any other forces?
No, it's self-contained. And friction?
The first box. Friction that one.
On the box.
Yeah.
All right, I'm gonna put it in here, and I'm gonna ignore it in just a moment. Well, F and
In front of the thing.
from the thing. You mean on the thing?
On the thing, yeah.
Okay. All right. Now, we've done the force diagram, we've done step number 1. Which way, now we get to the acceleration. This is just identifying the direction. This is not part of the force diagram, so I'm going to draw it apart from it. Which way is the 5 kilogram mass going to accelerate? If it is going to accelerate, which way will it accelerate?
Towards the 3 kilogram mass?
But is
Be
it-
more precise.
Is it accelerated? And like it's heavy? So it's not.
Well, we'll figure out if it's going to accelerate.
I mean, if it would, you would go towards the pulley.
Yeah, towards the pulley. You say towards the 3 kilogram mass, the reason I was picking on that one is that's towards the 3 kilogram mass.
No.
All right, so acceleration is that direction for this. And what about for this mass?
To the ground.
All right, I've drawn it off to the side, again, not part of the force diagram. Questions on the acceleration? All right, coordinate axes. When you're determining coordinate axes, I strongly recommend one of them be in the direction of acceleration, the other one perpendicular to that. So for this one right here, I have acceleration going that way, so I would recommend either I hat or J hat in that direction. Any preference?
Let's just keep it traditional.
All right, so I hat, I'm gonna call this I, so 5 hat, and then up or down, maybe J hat.
Yeah.
All right, over here, we do not have to use the same coordinate system. So it's, since acceleration, we're making positive direction there, I would make that a positive direction there. So I'm gonna establish down as my J3 hat. We could put in an I hat direction for that second one, but there are no forces in that direction, so it doesn't really do anything. So we did the direction of acceleration. This is direction. Coordinate axes we've done. And now decomposition. When you're trying to decide if anything needs to be decomposed or broken up into its components, the question is, are there any forces, so I got these 4 forces here, those 2 forces there, are there any forces that are not parallel or perpendicular or anti-parallel to my coordinate system?
The normal force on the rope.
I'm looking at just this mass right here.
No.
What about down here? Any of them that are not parallel or anti-parallel to our direction? All right, so we don't need to decompose anything in this problem. But don't worry, before we're done, we will on a different problem. So decomposition, done. Equations of motion. It is based upon F equals ma. So I'm just gonna write that down, F equals ma. I have one equation for each set of directions for each mass. So in this particular problem, I'm gonna have 3 equations. I've got 2 equations here, vertical and horizontal. I got 1 equation here, just vertical. This is the total force, and so I look at my coordinate system, and that tells me the positive forces. So looking at, and let's just highlight it. What are all the forces in the, well, let's see, we'll have an I5 hat, J5 hat, and J3 hat. There's gonna be my 3 equations. All right, so I5, what are all the positive forces?
normal force?
That's J.
Friction and tension.
Right? Jumping ahead. What are all the positive ones?
Just-
What are the forces in the positive I5 hat direction?
Just tension.
Yeah, this is the only one pointing in the same direction as that. So I put down tension. All right, what are all the negative forces in the negative direction?
Friction.
Minus the friction. Equals, so that's all the forces that are horizontal there, is equal to the mass of the 5 kilogram mass times the acceleration. Now the G, J5. What are all the positive ones?
The attention.
J.
Oh,
Normal.
No.
weight,
Yeah, why? Why is it weight, not normal?
that's good. Because the weight's pulling it down.
Yep. All right, so we have Y sub 5. No. Can't believe you wrote that. We have W sub 5 minus Y sub 5 is equal to M5 times. We are splitting this out by direction. We've established that the object, if it accelerates, is going to be accelerating to the right. So what is its vertical acceleration?
Wait, what?
I think we are comfortable with saying that the mass, the 5 kilogram mass is going to accelerate to the right.
Yeah.
There, and I'm asking, since this is my vertical equation, what is my vertical acceleration?
0.
And this is why we choose our coordinate system this way, is so that one of these equations is equal to 0.
Is that just because the normal force and the weight are balanced?
Yes.
Okay.
If they were not balanced, they would either dig into the thing or come off of it. And then the last equation. Someone want to take a shot at it?
I'm sorry, so
Oh, wait.
weight is greater than normal force, that indicates that the object that it's resting on is deforming?
It could.
Okay.
Why did we make the downwards motion I hat? Or did we not?
All right, my I's and J's, I feel like sometimes people get those mixed up. My I curls off to the right, my J curls off to the left, so
So
I've got J there,
that's just J3.
that's just J.
It's not I3, it's J3.
Yeah,
Oh, okay. More sense.
stupid letters where there's dot on top. What is the dot? Dot has a name. When I think of it at 2 in the morning, I'll call it chicken. All right. I could have made that I3 direction or some other, it's some direction. Not a problem with that. It just Michael wanted to go with the tradition. All right, so what is my J3 hat equation?
W3.
Minus the tension.
That's a,
Not an equation yet.
equals. Vertical.
Mass times acceleration.
F3.
Okay.
The acceleration is the same.
The magnitudes are, yeah, just the same. Three equations. Questions on these equations in motion.
How do we know that the accelerations are the same, or the same magnitude?
Ideal rope.
Oh, okay.
Since it doesn't stretch at all, if they're gonna move the exact same distance, the exact same amount of time, so the magnitudes will be the same.
So would we set the equations equal to FT and try to solve?
Yeah, we gotta do one other thing first before we do that. Yeah, yes, we will. So that's the equation solution, substitution. Now, when you're given a problem like this, at this point, its question is, do we have an independent equation for anything on here? And yes, we do. There's an independent equation for weight. There is an independent equation for friction. There is not an independent equation for tension. It is always problem specific. But weight does have a specific formula. Based on F equals ma, I take an object, if I drop it, the only force acting on it, ignoring air resistance, is the weight. So if I plug F equals ma into that situation, I have weight, and that's gonna be equal to the mass times, well, it's accelerating because of gravity, acceleration due to gravity. This is the independent formula, so we would make that substitution. So this equation right here, that really shows up well, is gonna become M3G minus the tension is equal to M3A. And this equation right here would become M5G minus Y5 equals 0. Questions before we simplify it?
It's not like MG3 or MG5. You have to put the subscript after that.
Wait, where did I mess up?
No, I was just saying, like, you said M3G,
Oh, that's M3G there, M5G there.
so you wouldn't put MG and then the number?
No, because G doesn't care which mass it is. Little g is because of the planet,
Okay.
or moon, star, whatever it happens to be. All right. Now, in this particular problem, friction is 0. And that's what these symbols right here are. This is telling us that friction is 0. That's a mu, mu, Greek letter. This stands for the coefficient of friction, coefficient of kinetic friction, coefficient of static friction. Kinetic friction, things are sliding. Static friction, they're not sliding. But we're ignoring friction for this part. So that is 0. And so I'm left with Ft is equal to M5G. And I'm gonna write Ft equals M5G. And now, however you want to solve it, at this point, I just add them because I got a negative tension and a positive tension. So if I just add the left-hand sides, tensions cancel out. I'm left with M3G. Right-hand sides, I got M3A plus M5. Oops. That should be A, not G. Plus M5A. I'm solving for acceleration. I'm going to factor it out. So I have M3G equals M5 plus M3 times A. So A becomes M3G divided by N5 plus N3. If this takes place on Earth, this becomes 3 times 9.8 divided by 5 plus 3. Which is 29.4 divided by 8. Which is something spectacular. a calculator that can whip that out real quick?
3.675.
So my acceleration, magnitude of my acceleration, 3.675, what?
J hat.
Well, we don't know
Or-
the units,
no.
do we?
Meters per second squared.
Those are the units. It better be meters per second squared, because everything we plugged in, we dealt with kilograms. That's meters per second squared. Yeah, so we have kilograms on the bottom, kilograms with the 3, kilograms would cancel, and you're left with whatever the units of this is, which is meters per second squared. Also, the acceleration, as long as we're dealing with SI units, it'll be meters per second squared. All right, questions to hear?
Yeah, where you got like the M3G equals M3A.
Plus M5A.
Yeah, can you show me how you did that again?
All right, so. Hopefully you'll remember what the problem looks like. So mathematically, I've got M3G minus the tension is equal to M3A, and tension minus, well, tension equals M5A. Now, if the math people have been lying to us, this doesn't work. I'm trusting that the math people are telling us the truth. What I did was, I took this, those are equal to each other, and I added the same thing to both sides. So on this side, M3G minus FT, then I'm gonna add plus FT. And on the other side, I have M3A plus M5A. I added the same thing to both sides because my second equation says that those are equal. The tensions cancel out, and what I'm left with is M3G